Have you ever asked yourself, what is a perfect number? Really? Well, for the past 2 weeks, I've been doing the most pointless project I have ever done to find out. If you clicked on this video, you may or may not have seen this Numberphile video. In it, I've seen a really cool idea. What if, after you calculate the sum of the factors of a number, you don't stop, but instead carry on to see what patterns would emerge? Now, I don't know about you, but I found this to be completely fascinating, but also incredibly arbitrary, which is why I did this. If you have seen my Call's Multiverse video, you know that I kind of specialize in this stuff, which is why I decided to do it again. So, here we go. Let's start with the basics. The default option is to just keep things as it is, which yields this. Now, I've got to explain what all of these things are. This is the graph of each number of 1 to 1000 plotted on a logarithmic scale. This is the number of stable patterns that are found in each path, be it either a perfect number or a loop, or that number escaping outside the bounds of the experiment by going through the top or the right edges. I call that a cutoff. And also, here are all the stable patterns listed out. And a number of times these patterns are seen within the 1000 different number paths. So, what do we see here? Here, there is a blob at the beginning, which kind of happens each time, because there are a lot of paths that take low number of steps to complete. There are also quite a few numbers that escape through the top, and also one really long path taken by a few numbers that doesn't escape through the top, that takes roughly 175 steps to complete. Also, each time you see this sharp drop-off in a path, that means that that path hit a prime number. And as for the stable pattern statistics, there are 6 stable patterns. The first perfect number, 6, has 13 paths going into it. The third perfect number, 496, has 5 paths going there. The amicable pair 220 to 84 has 3 paths going into it. The cutoff is exceeded 19 times. And weirdly enough, the second perfect number, 28, only has 1 number's path itself going into it. Kinda weird. But the vast majority, 959 paths, just go down to 0. And as for me, this is actually really boring. So, enter t. T is the value by which we change the sum of the factors on each step. For example, the t value of minus 10 means we subtract 10 from the factor sum on each step of the path. And the t value of plus 6 means we add 6 to each step on the path. You might ask, does this actually change anything? The answer is, it does. A lot. Here are the paths of each number from t of minus 13 to plus 13. First things first, you might notice that some of those paths are way different from the other ones. Those are the odd number paths. Now why would that be? Well, for that we have to consider even numbers. In the original universe, what happens when we have the factor sum of an even number? Well, the sum is almost always also even. Now why is that? For that, we have to consider prime factors of a number. If a number has any factors that are even, they of course won't change the evenness of the number. Now, as for the factors of a number that are odd, there are almost always an even number of them. If we just have one odd prime number, it will be an odd factor, and 1 will also be an odd factor. If we add another odd prime number, the first odd prime number, the second odd prime number, and their multiple, and 1 will be factors. Hence, there are an even number of odd factors, hence the number stays even. This can only change in 2 cases. If a number is a power of 2, meaning it has no odd factors except 1, and if a number contains the square of some odd prime number, meaning that only that prime number, its square, and 1 are the odd factors of a number. But it can't be multiple odd squares or an odd cube, then it will change back to even. But these cases are really rare. Now what that means is if we add an odd number to the factor sum, this means that if the number is even, then the next number in the sequence is almost always odd, which predictably results in fast decreasing sequences for each value of t, where t is odd. Now, as for the even values, their patterns are actually quite different. In some cases, like in minus 2 or plus 10, the paths still complete kinda fast, but in other cases, like minus 12 or minus 6, it takes quite a bit longer to complete. And in some cases, the numbers escape through the top border. This happens in 4 of the cases. 0, as we have seen previously, plus 6, plus 12, and weirdly enough, most commonly in minus 10. But how do the patterns differ themselves? Well, here is the number of different attractors in each t-value from -13 to +13. First thing to note is that it is at least generally true that odd values have less attractors than even values. Also, the original universe with t equals 0 also has less patterns than usual. And also, -12 seems to have absolutely loads of perfect numbers. Why is that? I don't know. But what about the values of attractors themselves? Well, here is the graph of each of the attractors based on the value of t. Red means perfect number, blue means a loop. Here you can see the curve of the first trivial perfect number, and for the negative values of t, it actually goes negative, at which point I stopped analyzing the data. But for those values of t where the first acceptable trivial number is not prime, we find that it is always a part of a loop. Also, you can see that there are generally fewer perfect numbers than numbers in a loop, except the t-values of -12, 0, and +1. That generally makes sense, as not only are perfect numbers generally rare and unique, but also for a loop I graphed each number in that loop, so while a single perfect number is graphed only once, a loop is graphed multiple times. As for -12, it apparently has loads of perfect numbers, and in 1, each power of 2 is a perfect number. As for 0, I don't know, it's just weird like that. As for the frequency with which numbers hit each path, I found for each value of t, the majority of the numbers result into just one pattern. Usually the smallest one, be it a loop or a perfect number. Also for the positive values of t, the ones which are loops are generally more frequent because they have more catchment area due to having more values in their pattern. As for the length of the loops, only the t values of +3, +9, +11 and +13 have no perfect numbers, only -11 and +1 has no loops, and most loops are either length 2, amicable pairs, or occasionally lengths 3 and 4. But there are a few values of t with ginormous loops. T equals +2 has loops of length 8 and 17, and t equals +8 of lengths 12 and 21. That's a lot. Well, this is cool, but I think it's not complicated enough. We need a second dimension. Enter R. R is the second variable I invented. R being the value each factor of a number changes by each time we do the calculation. So say the R value of +2 would add a 2 for each factor of a number that is there. And how does this change stuff? The answer is a lot. This is a graph of each combination of the values of R and t between -13 and +13. And what do we see here? Well, first things first, we see generally more interesting patterns to the top and slightly to the right, which makes sense, as if we add numbers instead of subtracting them, we generally get higher growing paths and more interesting patterns. Also, there are still the odd universes where the paths quickly degenerate to a stable pattern in the cases where R and t add up to an odd number, which would be the universes where the next number after an even is an odd. There are also some other cases where we observe such behavior. I classify those, at least pathwise, as type 1 universes, where the paths quickly degenerate to a stable pattern, with maybe 1 or 2 small exceptions. There are also type 2 universes, where the paths go down, degenerate eventually, but not after a lot of steps, such as +3 -3 or +2 +10. Then there are type 3 universes, where the paths either go down and degenerate very fast, or go up pretty fast, such as +3 +9 or +6 +12. Sometimes it takes way longer, such as in +3 +5 or +11 +11, but it still gets there. And then there are the type 4 universes, where the paths go, sometimes in large numbers, through the right border, and sometimes also through the top border, such as in +6 +8, +8 +2, or +7 +5. Fascinatingly though, most cases where the paths go through the right border are on the odd grid, and most cases where they go through the top border are on the even grid. I don't know why that happens. It is also worth pointing out the paths differ a lot between the same categories, as there are so many different and fascinating path patterns that I can't even show on the screen here. And then there is +12 +12. Even among the weird patterns, it is really weird. Why? Well, even in the different cases I've described, still only the minority of the paths go through the top or the right border. The majority still degenerates to a stable pattern. Except for +12 +12. Here is a graph of the number of paths that go through the top of the right border out of the total 1000 paths. Here is -10 0, which has the most paths in only t territory. Here is +7 -11, which is the second most cutoffs of any pattern at 372, but they're all going off the right border, not the top one. If you want to find a pattern with the second most cutoffs of the top border, you have to go to +9 +3 with 138 cutoffs. And here's +12 +12. With 955 cutoffs. Insane. But what about the number of attractors in each case? Well, here it is. Here you can see the cases on a combined value odd number grid generally have less patterns, and that generally when R and to lesser extent T are positive, then there are more patterns. Also here you can see is that 4 cases specifically have way more attractors than usual. Those are -12 0, -5 -1, +2 -2, and +9 -3. Why is that? Well, because this is the same group of numbers that fall into these 4 different groups. In fact, you can see that the groups have a pattern of down by 1 to the right by 7 each time. In fact, I have great confidence that this pattern continues to both the left and the right. Fascinating, I know. But what about the longest loop length in each case? Well, here it is in each case of R and T between minus 13 and plus 13. Here you can see is that path length of stable patterns tends to increase with R and to a smaller extent T when they are positive. Some of the longest path lengths though are ludicrously long. Notably, the second longest is plus 12 plus 10 with path length of 107 and the longest is plus 6 plus 10 with a path length of a whopping 140 steps. That's a lot. But what about the frequency in which each stable pattern occurs in each case? In only T, what we have seen is that most paths lead to just one specific stable pattern in each case, and this holds true here. In most cases, there is just one pattern that occurs most of the time, and there are lots of patterns that occur infrequently, and not a lot in the middle. But also, low occurring patterns generally tend to occur more frequently when R and T are both positive. But how about the attractors themselves graphed in 3 dimensions with both R and T? Well, here you can see a cool slope of the primary number of T plus R, but it is important here that I removed negative numbers from this visualization, so it would be, in fairness, more like this. Also, here you can see that with T equals 0 and T equals plus 1, 0 and 1 always show up as perfect numbers, in spite of different values of R here. But I hear you say, what is the highest number that shows up on a stable pattern? Well, there it is. So what did we learn? Correct, absolutely nothing. See you in the next one.